Bueno, ella, los mamás aritméticos lo puede hacer conmigo.
Sí,
Pero ella venía de cosas de extensiones, de funciones, pero de topológica.
Buenos días. Good morning to everybody. For me, it's a pleasure to be here with Gerald Beer or Gerardo Cerveza from the California State University. And I think that this is the 5th time that you give a talk here at the Mathematical Institute, from maybe the first time in 2000.
Maybe 19.
Yeah.
Maybe.
I'm not sure. 2008 or maybe 15 years ago or something like this.
Oh, no. It's certainly 2017. For sure.
Yeah,
maybe 2019.
So this is it's a great pleasure to have him with us. And this morning he's going to give a talk about making continuous function into Lipschitz function. So,
Thank you. It's great to come back to Polytechnica. On my keychain for my car, I have a Polytechnica medallion, which is plastic, but Jesus has given me a better one. I guess he assumes that the plastic one can't last forever, so he's given me one now that will last forever. So I think I'm going to, in the other talks that I've given in Spain, I've done it sitting down, and I feel that I do a better job for the first time in my life, so I'll try to continue with that again if that's okay. Okay, so this talk is reflects joint work with a Israeli mathematician, Zvi Arstein. Do any of you know this name? You don't know this name. This guy's pretty good. I think his best reputation is in optimal control, but it originated with a study he was doing on the so-called weak topology or the narrow topology on probability measures. I won't go into any of the details, but this had a practical point of departure. But what I'm going to talk about today is not. Is it okay? Okay, good. Oh, good. Everything I can see it better than I can see.
Yes.
Okay, so this will be a pure talk, and so it will be done in the context of metrizable spaces, and all spaces will have at least 2 points. And then for that, it's the basic assumption. So I'll start with a pair of spaces. X will be the domain and Y will be the target space. And X will be a metrizable space. So it doesn't have a metric associated to it. But Y will have a metric. Okay, so we'll be looking at functions from a metrizable space to a metric space. C of x, y is a set of continuous functions from x to y. And CB of x, y, that's the bounded continuous functions. We can talk about boundedness because y has a metric on it. X doesn't. We can't talk about the bounded functions C, B, Y, X. We can't do that at this point. Okay, so if you have a compatible metric with the topology, in other words, the topology that comes from the metric agrees with the original topology, we'll call, so now we have metrics on both spaces. We have the idea of Lipschitz, the usual idea of Lipschitz functions from x to y. And if a function is alpha Lipschitz, in other words, alpha is a Lipschitz constant, doesn't have to be the smallest one. And alpha is 1, the function is called non-expansive usually. And Lipschitz functions are, of course, uniformly continuous. So here's the basic question to start with. So this is what Zvi asked me about. He knew that I work with Lipschitz functions, and he thought I might know something in the literature, but I didn't know. Suppose I have a family of functions from x to y. So we're back to the situation where x doesn't have a understood metric, but y does. So, for example, you might be looking at real valued functions, and you want to use the usual metric on the target space. But the question is, can we find, or when can we find a metric on x such that all the functions are Lipschitz? Thus the title. Okay, so, well, there's sometimes we can't. So if we have a finite family of continuous functions, f1 through fk, we can, again, y has a metric understood, rho. There's an easy way to define a metric on x such that the functions are Lipschitz, that one. So if the sum there represents a continuous pseudo-metric on x, and if I add that to the metric, then I have a compatible metric. And the original function, each of the original functions, f1 through fk, is Lipschitz with respect to this. Because, in fact, if I look at rho of fn x, rho of fn w, that's less than or equal to the right hand side for any particular n. So these functions are all, in fact, non-expansive. Okay, so this metric d1 does the job. But everybody knows this. There's nothing original about that. I'm just giving you an example. The next example is even more elementary and tangible, but I don't think people so much have thought about this. I'm not saying that this is a new idea, but still it's something that should be in an analysis book. So in a first course in analysis, so let's look at the quadratic functions from R to R. So f of x looks like ax squared plus bx plus c, where a is not equal to 0. You have this word in Spanish, quadratic function? Something like this. Okay, so this, of course, if I have the usual metric for the target space and the usual metric for the domain, these families none of these functions are Lipschitz. Yeah? But I can remetrize the domain so that they are easily. Replace the usual metric, the Euclidean metric, by that. So I add this perturbation factor. Okay? And with this new metric, all of your quadratic functions are Lipschitz because of this line here. F of x minus f of w is ax squared plus bx minus aw squared minus bw. And then you get this using the triangle inequality. And then you get this inequality, which shows that absolute a plus b, absolute b, is a Lipschitz function for that quadratic function. Well, that's kind of fun. I think that should be an exercise in a book. It's nothing hard. Okay, so we know what the basic question is, but we probably have no answer, or even ideas of some sufficient conditions which will make it true. And when Zvi and I started, we had no idea about anything, but within a week and a half, we had characterization theorems. I can't explain how this happened. We just chose to do the right thing. And a key idea in the analysis is equicontinuity. So where have you seen the idea of equicontinuity? In what context? in analysis or topology. You have seen this. What theorem does this come up in?
Differential equation.
Arzelà-Ascoli theorem. Maybe in differential equations, but most famously in the Arzelà-Ascoli theorem, which involves compactness criteria for continuous functions equivalent to the compact open topology. Okay, so here's the definition. I took this out of Degunji, the topology book by James Degunji, for pointwise equicontinuity. And this is what's used in the Arzelà-Ascoli theorem. Okay? So it's right there. That means that, again, you have X metrizable, not with a metric, and Y as a metric. So it says that given any epsilon, you have this family omega of continuous functions. We'll always call it omega. Given any epsilon at any point X, there's a neighborhood of X. So I'm not using a metric on X, and so I have just an open set containing X. So it's that for any point W in any function in the family, W being in that neighborhood, the distance between f of X and f of W is less than epsilon. Okay? And to talk about stronger notions, you really need to have a metric on X or a uniform structure. But we're going to keep things, we're not going to talk about uniformities at all here. So here's this statement about sometimes it's called the Arzelà-Ascoli theorem, sometimes it's called the Ascoli theorem. I'm not arguing for one over the other. But, so let's talk about some stronger notions. I feel much better sitting and talking than standing and talking. I'm much more relaxed. Because when you get older, you're worried about falling over. I mean, without being drunk. This is true. So suppose now X has a metric D. Okay? So we could have the neighborhood W being thought of as a ball. And it may be for a given epsilon, you can use the same ball at each point. This is called uniform equicontinuity. Okay, so that's what I've written. Where's the red thing? Right there. That's uniform equicontinuity. Okay, so that implies pointwise equicontinuity. If the domain is compact, then pointwise equicontinuity gives you uniform equicontinuity. But it's true more generally, actually, in a class of spaces called the UC metric spaces, which this guy knows about. And these aren't ever in books either, and they should be. But I'm not going to stop to talk about what they are. And then even stronger idea is the idea of an equi-Lipschitzian family. Remember, we have metrics now. So this means that each function is Lipschitz, and you use the same Lipschitz constant for them all. That's stronger than uniform equicontinuity, which is stronger than pointwise equicontinuity. So I of course don't bring this up unless it plays a role in the basic question, and it's the key idea in the basic question. So it's nice to see equicontinuity come up in a different context than you expect. Okay, so now we'll look at the main results. Okay, so the main result is we're going to characterize, in the case of bounded continuous functions from X to Y. Remember, X doesn't have a metric. The existence of a compatible metric on X, such that we're going to characterize the subfamilies that are going to be Lipschitz with respect to some remetrization. Okay? And the characterization doesn't work in C of XY, just CBXY. I don't know the answer for C of XY. And I wanted to show you that it's not true that, in general, CB of XY itself admits a good metric so that all the functions are continuous. So let's suppose I have a limit point in my space, an accumulation point, a limit point, call it P. And I take any metric which is a compatible metric for the topology of X, call it D. This function with respect to D, this is bounded and one Lipschitz. No, it's not. I'm sorry. I'm not saying, didn't say that right. It's not. It's bounded and it's uniformly continuous. But it won't be a Lipschitz function with respect to D. So no matter what metric you take, there'll be a bad function that cannot be made a Lipschitz function. So it doesn't work in general. You have to work with subfamilies. You look like you want to ask a question. Yeah, no, you're good. Okay, so the first thing is a tool proposition. So it is something that allows you to do things rather than a final result. And this is key also. Okay, suppose I have a metrizable space and a metric space. This is the context we're talking about. And for each n and n, we have a subfamily of the bounded continuous functions, for which there's a good metric, Dn. So in that subfamily, all these things are Lipschitzian. The metric's bounded, Dn. Then I can make a metric on X, which is also a compatible metric and bounded, such that all of the functions are Lipschitz. Okay? It's not hard. You know, if you're an analyst, you do something like this: a 2 to summation 2 to the minus n something. That's what you think of doing some way, because you have a countable number of things, and you combine them in that way. Some people in America would say, well, it's a 2 to the minus n proof. And this is how you do it. Okay? So this represents the diameter of the space with respect to dn. Remember, dn's bounded for each n. And so if you look at each of these things in the series, this over this is less than or equal to 1. And so the series is dominated by the series sum to the minus n, so it converges to a number less than or equal to 1. And so this is a bounded metric for which the diameter of the space is less than or equal to 1. And it's easy to show that, remember, all the dn's are equivalent metrics. They're compatible, so they're equivalent. And this metric d star that I form here, it's easy to show, it's just a standard exercise, that it has the same convergent sequence as each of the dn do. And therefore it itself is compatible too. Okay? So now I want to show that, and it's bounded, and so now I want to show that each of my functions that I have in each omega n is Lipschitz here. Well, I mean, if I have a function f which belongs to omega n, well, then rho of fn of x, rho of f of x, rho n of f of x, f of w, will be less than or equal to some multiple of this. Okay, so whatever that multiple is, that's the multiple. It's going to be less than or equal to that multiple of the entire series, because it's so for one of these summands. And so that shows that each fn is Lipschitz with respect to that metric. So I'll give you an immediate application of this to what I consider to be a folk theorem. Here's my definition of folk theorem. A folk theorem is a theorem that you expect many people know, but you have no book where you can point to or paper that you find it. That doesn't mean it doesn't exist in a paper or book, but I don't know of one. So, or you can say it's a theorem which is not yours, with probability 1. Okay, so let's look at this. It's an interesting fact, though. Again, it's something that should be, I feel, in textbooks as an exercise. I mean, you can give a direct proof without using the tool theorem. And so suppose I have a sequence of bounded continuous functions from x to y. Okay? Then you can find a bounded metric on x such that each function is a Lipschitz function. Okay? And so you can, you could sit down there and without the tool theorem and prove this. Again, using a 2 to the minus n argument. But let's see how it follows from our tool theorem. Okay, so I'll let omega n just be the single function fn. Okay, and I want to show that's bounded with respect to some bounded metric. Well, I start with a metric, a bounded compatible metric d on the space. And then I add that to it. If it's a bounded function, this is a bounded metric. And just as before, Fn is going to be Lipschitz with respect to that metric. And so now you apply the last result because you have a countable family. And that's it. That's kind of cute. But again, you don't, need to do it this way. Just do it. Okay, so here, this is the key result. It's not the main theorem, but it's really the key result. It's very elementary, but completely unexpected. Both the result and the proof. There's nothing advanced I'm going to be using here, but I've never seen anything like it. So I don't know how I came up with it, but I did. Okay, so here's the theorem. So I have a family of equicontinuous functions from x to y. Pointwise equicontinuous. Then I can find a bounded compatible metric on the domain. It's compatible with the topology, since all the functions are Lipschitz. You probably have no idea how I'm going to do this. It's not a 2 to the minus n proof. Okay, so we're going to use some facts about pseudometrics. We already remarked that if we add a pseudometric to a metric, we get a metric. Okay, that's one thing. Second thing is, if I have a pseudometric on x, and I take the minimum of the pseudometric in 1, then I get a pseudometric. This has nothing to do with topology, these things I'm saying. I'm just talking about metrics and pseudometrics. And the third thing is if I have a bunch of pseudometrics which are all bounded by 1, then the supremum of the pseudometrics is a pseudometric. One is nothing special about 1, but that's what I'm going to use here. Okay? So these are also mentioned in this topology book by Degunji, these facts. But I knew them anyway. I just I wrote them out and I thought, well, this is what I want to do, and so I better verify these are pseudometric. Okay, so we start with a bounded compatible metric for x, and here's our guy. This is how we're going to define this good metric. I'll call it D1. I mean, this is going to be the metric such that all these functions are Lipschitz with respect to. All right? So if I look at rho of fx, f of w as a function on x cross x, this is pseudometric. And then I take the minimum of that in 1, that's a pseudometric, and then I take the sup of those over all f and omega. So I get a pseudo-metric. And I add that to a metric, so I get a metric. And it's bounded by d plus 1. Okay, so we got a bounded metric. Well, we got to show two things. We got to show that it's compatible with the topology. In other words, equivalent to D. And we have to show that all of our functions are Lipschitz with respect to this. Oh. Let's do that. Okay, so anyway, this metric D1 is bigger than D. So to show it has the same convergence sequence is all I have to show if I have a sequence which is D convergent, then it's D1 convergent. Okay, so I start with a sequence. Did I say series? I meant sequence. If xj is a sequence which converges to x in D, then I got to show it's convergent to x in D1. Okay, so I'll start with a epsilon, which is between 0 and 1, less than 1. And D is compatible with the topology, and we have pointwise equicontinuity of omega. We can choose a neighborhood of x such that whenever I take a point in this neighborhood, two things happen. The distance from x, w to x, is less than epsilon over 2. So the neighborhood's contained in the ball with respect to d over radius epsilon over 2 about x. And secondly, by the pointwise equicontinuity, whenever f belongs to omega, you get this inequality. That's pointwise equicontinuity looking just at this point x. These just two things. I can do that. Well, eventually xj lies in w because xj converges to x. And since epsilon over 2 is a half, you get this inequality. Because each one of these guys here, by the pointwise equicontinuity, is less than epsilon over 2. And so when I take the minimum of 1 in that, I get epsilon over, something less than epsilon over 2. And so when I take the sup, I can't get more than epsilon over 2. So that eventually you have d1 xjx less than epsilon, because you can make the first part less than epsilon over 2 as well. In fact, I did. In other words, the dx xj is less than epsilon over 2 as well. Okay, so that shows that you have compatibility of the metric d1 with topology. But now the Lipschitz part argument, you look at this and go, what is this argument? It's elementary, but what's going on? So I'll start with a g and omega. I don't want g to be f because f looks too generic. And let x w be an x. So I want that the distance between the function values to be less than or equal to some constant times the distance from x to w, the d1 distance. Well, I'll consider two cases. First, though, I'll let m of g be the diameter of the range. G is bounded, so it's a finite number. Okay, so first case, the distance between the function values is less than 1. Second case will be the distance is greater than or equal to 1. In the first case, the distance from g of x to d of w, well, it's less than or equal to that because I just added something non-negative to the left-hand side. And this guy here is one of these things. I mean, it's one. I'm not saying it right. The distance. This minimum is this because this is less than epsilon over 2. The minimum is this thing, and then this is an estimator for the things you're taking the sup over and forming d1. So this is less than or equal to d1 of xw. So So in that case, 1 is a Lipschitz constant for the points where the distance is less than 1 between the function values. The other possibility, the distance between the function values is greater than or equal to 1. Well, then, if that's true, then one of these minima is going to be 1. And so then I take the soup over things that can't get bigger than 1. So I get d1 of xw is going to be equal to dxw plus 1. So you get at least 1 for the distance between x and w. So let's look at these difference quotients. Rho of g of x, g of w over d1 xw. Well, the top is less than or equal to the m of g, by the definition of m of g. And d1 of xw is at least 1. So if I make the denominator smaller, I get a larger fraction. So that says that rho of g of x, g of w is less than or equal to m of g, d of 1 of xw. So in either case, if you use 1 plus m of g, that'll work as a Lipschitz constant. And that's it. Totally elementary, but the word non-standard means something different in mathematics, but it's not a usual proof that you see in analysis. Okay, so again, I want to remark that a pointwise continuous family of unbounded functions need not be Lipschitzian with respect to any compatible metric on x. And I don't want to go through the example. It's elementary, but I'll tell you what x is and what y is. So y is the reals with the usual metric, and x is the natural numbers with the discrete topology. And you can't find any metric for that space. Every function is continuous. And so the unbounded continuous functions are just the unbounded functions. And whatever metric you choose on x, you can find an unbounded continuous function, a non-Lipschitzian unbounded continuous function. It's hard to say these things sometimes. I mean, some of the expressions involve too many words. Okay, so now we'll come to the main theorem. But there's another theorem that you may think should be is a Mainer theorem. That's not an English word, but you know what I mean. More main. But I think of this as the main theorem, because this is related to the question we were initially asking. So the main theorem ought to characterize those subfamilies of CBXY for which there's a metric on x such, and it'll be a bounded metric actually, you can choose to be, such that the functions are all Lipschitz. Okay? This is it. Okay, first condition, there's a bounded metric on x such that you can do this using D. And the second condition, there's just some metric. And the third condition is the key condition. Omega is a countable union of pointwise equicontinuous families. Okay? So this is really the answer to the question. So it's a simple answer, but it's not expected, you know. I don't think it's expected. If you don't know anything about it, about the subject, and we sure didn't. But so 1 implies 2 is trivial. Here D has to be bounded, here D can be anything. And 3 implies 1 follows from our 2 key results. Beat that preceded. And for 2 implies 3. Well, and you know, when we prove these two things, we didn't think about that these conditions could be necessary as well as sufficient. I mean, we just did it. We had so little hope that we could actually solve the problem, but we ended up solving the problem by getting enough sufficient conditions. No, I didn't say that right, but you know what I mean. I mean, maybe am I talking about? Yeah, I mean, anyway, I'm having trouble speaking. So suppose I have this. No, I want one to imply, one implies two, two implies, three implies one. I want two to imply three, right? Right, that's what I want, that's what I'm saying, two implies three. So I have this good metric, not necessarily bounded, but I have a good metric such that all my functions are Lipschitz. And where do I come up with my omega n? Well, omega n will consist of the functions in omega, which are n Lipschitz. Okay? If I have a family of n Lipschitz functions for a fixed n, that's equi-Lipschitzian. So it's uniformly equicontinuous. So it's pointwise equicontinuous. And that's it. That's very simple. There's nothing hard about this. Okay, so now we're going to come to a related problem, which seems to be of more interest. So in 2019, there was a monograph published by 3 Romanians called Lipschitz Functions, the Springer monograph. Have any of you seen it? Well, you've seen it, good.
I studied a lot, this book.
You have studied it a lot?
Yes.
Okay, so really?
We were involved in this
Okay, so in section 3.2, they address the following question. Suppose x and y are metrizable. Can I find metrics? So neither one has a metric. And I have a family of continuous functions between them. Can I find metrics on the domain and the target space? So I have freedom in both spaces, since it's a family's a Lipschitz family. Well, they got nowhere in terms of positive results. They did nothing. But they came up with a counterexample saying in general, you can't make the entire family of continuous functions Lipschitz. And the spaces they looked at for the domain space, they're both subspaces of the line, topological subspaces of the line. The rationals is the domain, and closed 01 is the codomain. And they can't do that. Well, that's something. I mean, it's a contribution saying you can't always do it. Okay, so let me try to pronounce these and you correct me. This is my American guess. Kobzash, Nicolescu, Nikolai. I might be close.
They are Romanians, so probably we have no idea.
They would be angry at it. They'd be laughing at me. But this book is a very good contribution. You know, it's very interesting.
We like this book.
Okay.
But I know this Stefan Kosas is always complaining because we never put this little thing under the S. You know, at the end of the name, there is a
little cedilla. Looks like a French cedilla. So I try to do this.
Yes.
But the same problem for Spanish writers. You have like, you have accents on Sanchez. You know, why do you need that? Why do you need that?
You know,
Well, I'm just saying Americans have problems with just as many problems with Spanish. You know, they go, why should you have some problems? Okay, so anyway, let's solve their problem from this last theorem. Just immediately. There's nothing to do. In a way, I'm surprised they put this even in there because they weren't able to say so much, positively.
No idea. Probably they were trying to get a complete picture, and it was a hole there.
They wanted to express the whole,
Yes.
hoping somebody would do this. Well, now they've succeeded. But I maybe I have not written Kopsach yet, but I probably will.
Okay. I mean, he's a very nice man. Did you ever met him?
No.
He's a nice man.
I know that Nikolai comes to Complutense some. I know that. That's where I first saw the book, because she gave it to Jaramillo and his wife, who is his wife. You know her name?
No.
Maribel. And Maribel is my main co-author. Okay, so here is the theorem. This answers the question that was raised by these three authors. So you have X and Y metrizable. You don't have metrics on either one. When can you find compatible metrics such that things go well? Well, maybe I'll let you think about it. It's almost immediate from what follows, what preceded, rather. Oh, I mean, the idea is let's just look at 3 implies 1. I mean, that's you want to see, that this condition gives you the existence of this. But actually, both metrics are going to be bounded. And what you do is simply, if you have you have a metric on y, you don't care about x, such that the functions are pointwise equicontinuous. Okay, you don't need a metric in x to talk about that, but you just have this good metric rho star on y. Well, if you replace rho star by the minimum of 1 and rho star, then you still have a pointwise equicontinuity. But now all of your functions are bounded, and so you can apply the last theorem. I wanted to just talk for a minute about, let's go back to the quadratic functions. Okay, we know that they have to satisfy this condition. Quadratic functions aren't bounded, so they don't really fall into the framework of the first theorem. But we know that if we use the Euclidean metric on the domain and this other little, the distance between x and w is absolute x minus w plus absolute x squared minus w squared, then we get a Lipschitzian family. Okay, so it fits. So you must be able to decompose it into a countable union of equicontinuous families, pointwise equicontinuous families. So let's just talk about how to do that. And so this doesn't look like a Q to me, but this is what the math script or whatever it is gives me, a Q. So Q is the quadratic functions. Okay, so the way I did this, it was easy for me to do. I mean, it's something really an undergrad, well, maybe a first-year graduate could do. So I think of each quadratic function as a 3-parameter family. So, typically f of x equals ax squared plus bx plus c, yeah? So, but we'll complete the square. I don't know what the expression is in Spanish, but in English, complete the square. So we rewrite the function in this form, so. Say it?
Completar el cuadrado.
Okay. Yeah. This thing doesn't seem to work anymore. Well, I don't care, but anyway, so we write it like that, okay? So this gives it makes it more geometrical. So what you're doing is translating the standard parabola ax squared, x0 to the right, and y0 up. That's what you're doing, okay? So it makes more geometric sense. And after you do that, here's what you do here's how you get omega n. Omega n consists of the functions where the lead coefficient a is between minus n and n, and the x0 is between minus n and n, and the y0 doesn't count. And it's easy to show, it's a just a routine exercise that I think a first-year graduate student can do to show that that's going to be pointwise equi-continuous. It's not uniformly equi-continuous, but it's pointwise equi. So the last thing I want to do, I want to mention this. You know, our theorem says stuff about bounded metrics. So let's suppose we could, I mean, the way I do this here, you know, it doesn't involve the metrics that you're using. It just you know, you're just showing, it just shows the pointwise countable union of pointwise semi-continuous families. But let's suppose that the metric on X that you use is bounded. Well, that will force the metric on Y to be bounded. Because let's look at the squaring function, x to x squared. Okay, so if D is bounded, that function has to be a Lipschitz function. And so the image of the range of the function will have to be bounded also, because the Lipschitz functions map bounded sets to bounded sets. And so 0 to infinity has to be bounded in this metric row. And similarly, using minus x squared, the range of the function has to be bounded, since it's Lipschitz, the domain is bounded. So minus infinity to 0 is bounded in this metric row. So the whole line is bounded. Okay? So if you start with a good metric on X, which is a bounded metric, the metric on Y has to be bounded as well. And that's guaranteed by this theorem, that you can find bounded metrics for which this is true. All right, so now we come to the part of the talk. I've talked 50 minutes, right? Yeah, so now that I want to talk about something nothing to do with this. I want to come back to the Arzela-Ascoli theorem. So this is a pedagogical point. It's my feeling that for many analysts, they know the Arzela-Ascoli theorem, they see statements about it, but they have no idea what it really means. They don't take the time to read the proof, or they don't like the context of the proof because it involves terminology which is outside of what normal analysts work with. And so I want to talk about what it means for analysts. Okay, a version of it that it can be totally understandable by any analyst, and they won't say, well, I don't want to look at this stuff. I don't care about uniform spaces. I don't care about case spaces. I don't, they go have a beer or something. Okay, so a version of the Arzela-Ascoli theorem for analysts. Again, you may want to call it the Ascoli theorem. I don't care about it. And so this is adapted from the discussion in the topology book by Willard. Willard's actually a Canadian mathematician, not an American mathematician. And I feel this is the best book to learn topology from. Easily, no question. He doesn't have to agree, but he's nodding his head, so it's... Anyway, my co-author, Mary Bell, absolutely agrees. So I'm not going to talk about any terminology that would put off an analyst. And I won't talk about set open topologies. The compact ocean topology is called what it is a particular set open topology, but I'm not going to talk about that. Okay, but I will talk about some things that I want to review. All right, so the context is functions between metric spaces. X tau, I'll show her the metrizable space, and then we'll give the target space a metric. So a local base for the topology of uniform convergence on compact subsets. So F is a particular continuous function. Consists of those functions G which are close to F on K. Okay, so there's two parameters. The closest is represented by epsilon, and K is a compact set. Okay? So that's what it is. And something that some analysts know, this goes back to a functional analyst, Richard Ahrens. So there's Richard Aaron, and then before that there was Richard Ahrens, A-E-R-E-N-S. So it's like the Mackey-Ahrens theorem you've heard of. But he proved that in the 40s, he proved that this topology is metrizable if and only if the underlying space is hemi-compact. And in the context of metrizable spaces, that means that it's locally compact and separable. Okay? But he did it more generally. At that time, he was working with Dugunji. So, okay. So everybody understands what this topology is. From this point of view, I don't care what you understood before or didn't understand before. So here's the Arzela-Ascoli theorem. So this is exactly from Willard, except his context is more general. He calls it the Ascoli theorem. So let X tau be metrizable and Y rho be a metric space. So this is like the context of our talk here, right? And I have a subfamily of C of X, Y. It's going to be compact in the compact topology of uniform convergence on compact subsets. I'll call it tau CO. If and only if these three things are satisfied. So the first condition says that omega is closed in the topology of pointwise convergence. The second thing says that if I look at the images of a point, the family of images of any particular point, it has compact closure in Y. I mean, f of x sits in Y. If I let f vary, then I get a subset of Y. I want the closure to be compact. And the third condition says, whenever I have a non-empty compact subset, it should be of X, sorry. Then omega is pointwise equicontinuous when restricted to K. Okay, this is necessary and sufficient for compactness. In some books, they'll just give sufficient conditions. I'll let you look, maybe you want to ask something or say something. Okay, so there's these things, and probably you have all looked at a statement like this or something similar and gone, okay, maybe I'll use that someday for something. So I want to talk about what this means. So in America, there's a slang expression. It's called "what up." So there's no verb in there, and they may say that young people use this. What up? So that means what's going on, what's happening, what up? Have you heard this?
Yeah.
Oh, good. Okay, so I'll make 3 points. The first point is I think really the key point. If you have a family of C of X, Y, which is compact in tau CO, then tau CO on this family must be exactly the same as the topology of pointwise convergence. That's the key point. And here's why. If omega is compact, let's look at omega equipped with tau CO and consider the identity map from that to omega equipped with pointwise convergence. Topology of pointwise convergence. Well, the domain space is compact, and the target space is Hausdorff. And if you have a continuous function, it's continuous because the target space has a weaker topology. It's the same. The underlying set is omega, but on the target space you have a a weaker topology. So you have a continuous function from a compact space to a Hausdorff space. It has to be a homomorphism. That's the key point. People do, they look at this and they don't even think about that point. But Willard makes this very clear. None of these ideas originate with me. I'm just trying to re-explain what Willard explains to the reader who's willing to read it. Second point, conditions 1 and 2 together characterize compactness of omega with respect to the topology of pointwise convergence. The topology of pointwise convergence is really the product topology. And you're thinking of, you can think of the product of the closures of f of x, f and omega. Product of those. And this sits in y to the x. But the product of those is a product of compact spaces. And so by the Tikhonov theorem, 1 and 2 will give you compactness. Okay? So that's it. So where does the equicontinuity come in? Equicontinuity, pointwise equicontinuity. You should say pointwise, because there's a difference between pointwise and uniform. But not really in this case, because when we talk about pointwise equicontinuity on a particular compact K, that's the same as uniform equicontinuity. I'll just point that out. But this condition 3 in conjunction with 1 and 2 is exactly what you need to show that the compact open topology and the pointwise topology agree. Okay, so this is the idea that he has, and I think most topologists think of when they approach function spaces with topologies stronger than the topology of pointwise convergence. You got to have conditions. You've got. If you want to show compactness, it's going to then the topology, the space with the topology reduces to the space with the pointwise topology. So you just use the criterion you use for compactness for the pointwise topology, and then figure out what it takes for the two topologies to coincide. So this is the standard point of view, but I believe there are other productive points of view, and that's what I hope to work on in the future. It's good to be done. Yeah.
Okay, thank you for your talk. Very interesting. Now, any question?
Oh, one more remark. I've submitted this paper to Roxanne.
Okay. Spanish, no?
Of course.
Yeah.
Do you have any question or comments about the topic?
Yeah. Yes.
I would like to ask, so if you consider the same problem you were considering at the beginning about families of functions that can be turned into Lipschitz functions, so what about if you want to make them uniformly Lipschitz or equi-Lipschitz?
Well, we have some things in this paper about that. I just didn't have time to include it. But I'll send you, give me your email address and I'll send you a copy of the paper. Or I'll give it to you. I have a pen drive on it. But that is considered. Yeah, we have 2 results on that. So he's asking really a very natural thing. You don't want the functions just to be Lipschitz, but you want them to be Lipschitz with all the same Lipschitz concepts, equi-Lipschitzian. You'll like, they're 2 little results, but I think you'll like them.
If this is, is your preprint on archive or something, then I can...
No, I don't do that. I'll just give it to you. I believe in getting papers by asking the authors for the papers, or on the other hand, giving people who you think might be interested in your paper. I don't want to do too much technology. I refuse to do this shit. What's this other thing where people, you see how many hits you get? What is this? What is this service? It's
Which one?
ResearchGate?
Yeah, something like that. I don't want to. Yeah.
a little bit stressing.
Yeah, I don't, who cares? I don't want these notifications that somebody looked at my paper. Well, here's a question that I thought somebody would ask, that I'm not going to look at, because enough is enough already. You might ask, what if we have a fixed metric on X, but Y is metrizable? Can you find a metric on Y? I don't have any particular interest in that question. I just don't. And anyway, I think it's good to leave something open for others to do.
So, any more questions? So, thank you, Jerry.
Thank you for coming. I hope I'm not so old that I can't come again. It's no joke, though.